Hello. In this video we're going to talk a little bit more about our Unit 2, Part 2, this time Lesson 2, inside of our calculus class. And this is where we get to introduce our product and quotient rules. These are rules number 21 and 20, respectively, in our list of rules that I'm asking you to memorize. And so here we'll get a chance to see how they work and why we use them. Rather than prove these derivatives, I thought I'd just kind of give you an anecdotal reason why we have to use them. Now, let's say we've got a function f that's defined as x squared minus 2, and we've got a separate function g which is equal to 3x minus 7. The combination of the two functions, when they're multiplied together, f times g, is going to produce a third function that we're going to call h. And so since this isn't too challenging, we could simplify h in terms of just x. H of x is equal to f of x times g of x, so what I'm really asking you to do here is to take f of x, which is x squared minus 2, and multiply it by g of x, which is 3x minus 7. If we FOIL and combine like terms, actually there are no like terms here, looks like 3x cubed minus 7x squared minus 6x plus 14 will do it. So no like terms to combine, but in a sense what we're saying is that h of x is now equal to this, which is a result of f of x times g of x. Alright, so now that we've got h of x in terms of x, we won't always have to do this, but to prove my point we're going to. Let's go ahead and calculate the first derivative. Well, h prime of this polynomial, which follows a series of power rules, is going to look like 9x squared, because again we're taking the power of 3 and multiplying it by this coefficient and reducing the power by 1. For our second term we'll end up with 14x to the first power, and for our third term minus 6. We haven't seen this yet in class, but I'll point out now, when we have two apostrophes, or perhaps a quotation mark, this is what we call our second derivative of h, and you may have guessed it, the second derivative of the original function happens to be the derivative of the first derivative. So the derivative of a derivative. So we'll just keep moving down the list here. We'll talk about applications of this at another time. But here's the second derivative of the original function, which happens to be the derivative of the first derivative. Instead of showing h with 3 apostrophes, that could be a bit distracting when we start getting to 3 or more of these apostrophes. Sometimes you'll see the notation where we actually indicate the derivative here with a number. So the third derivative of our original function happens to be the derivative of the second derivative. In this case is the constant 18. Now what I'd like for you to focus on is this first derivative here. This is the derivative of h, and I know that this is correct because we were able to very easily calculate what h was in terms of x. So rather than thinking of h in terms of f of x and g of x, we have h as it's written based on the letter x only. So this is the derivative that we're after, and some of you might be thinking, well, if h of x is equal to f of x times g of x, wouldn't the derivative of h just be the derivative of f times the derivative of g? I mean, it works for addition and subtraction. Why wouldn't it work for multiplication? Well, let's take a look. F prime of x would be the derivative of this guy, and the derivative of x squared minus 2 looks like 2x to me. And the derivative of g of x, well, here's g of x, and its derivative of a constant function, is just the slope, which is 3. And so, again, if h of x is equal to f times g, does h prime equal f prime times g prime? Well, we just said that h prime was 9x squared minus 14x minus 6. That's what h prime of x is equal to. And then f prime of x we said was 2x, and g prime of x was just 3. So does h prime really equal f prime times g prime? And the answer is Resoundingly no. They're not very, very close at all. They do not match. So don't fall into that trap. When we're dealing with large combinations of functions, specifically ones that are combined with multiplication, we cannot simply find the derivative of each of the components and multiply the derivatives together. It will not produce the true and accurate derivative of the combined function. So this is where that product rule from our derivative rules comes into play. The notation on our handout says the derivative with respect to x, using Leibniz notation here, the derivative with respect to x of two functions, f and g, multiplied together, would be the derivative of the first function times the second function originally, plus the first function in its original form times the derivative of the second. And so a trick that I share with students to teach this process in the beginning, before you start to internalize the process, is to do the following. Let's identify two functions, f and g, and we'll talk about how we can combine their derivatives in just a second. So in our example, f we said was x squared minus 2, and g we said was 3x minus 7. So if my job is to find the derivative, in this case it's of h, because h is the product of f and g. If I needed to find the derivative of h, I need the original function g times the derivative of f plus the original function f times the derivative of g. And it's pretty common to use this notation for an abbreviation here. I didn't include the x component of the function notation, and that's okay. So if we know that that's our objective, is to find the derivative of h, this preliminary work, which is sometimes done mentally, is done off to the side here. I'm just going to jot down what f prime was. We said that that was 2x. And what g prime was. We said that that was 3. And now I want you to imagine these cross products. This is going to help us not only with the product rule, but also our quotient rule. These two cross diagonals, as long as you build your formulas off to the side like this, these two cross products are always going to multiply together. So our first component is g times f prime. Well, we said that g was 3x minus 7. We said that f prime was 2x. So I'm going to jot that down. G times f prime. To that I will add f, which was this guy, x squared minus 2, times g prime, which was 3. And this result doesn't look like our answer from before just yet, but after we distribute, which is kind of awkward because the coefficients are at the tail end of the binomial. But again, after we distribute, we'll be left with 6x squared minus 14x plus 3x squared minus 6. And when we combine like terms and write in standard form, we end up with 9x squared minus 14x minus 6, which is the same result that we got all the way back here. Now, if you recall, this result was obtained by first multiplying the two functions together to obtain the new function in terms of x, and then we found the derivative of that. Down here, we found the derivative of the subfunctions, or the component functions, and combined them using the derivative rule. Now that process, using the derivative rule, is going to be helpful when we start encountering more complicated equations. If we can generate a function by foiling it together, that would be perfectly fine, but sometimes that's not always going to be the case. So here's an interesting pair of functions. We're being asked to find the derivative with respect to the variable v, and this is the function here. This outer parentheses identifies our function. So hopefully you can see right away that this function is composed, not composed, but it is a combination of two other functions, and we'll call this guy this guy f and this guy g, just to make things a little bit easier. So if we say that f is the function v squared and g is the function 2 square root v plus 1. Well, here we go. We've got our two functions that are multiplying together. That's what made this large outer function. What we need first is the derivative of f, which is simple because this is our power rule. We also need the derivative of g, which is not quite as simple because we've got this square root involved. Well, rather than trying to derive this rule, this derivative rule, every time you need it, we can refer back to the derivative rules that we memorized, and this one happens to be rule number 9. In rule number 9, we said the derivative of a square root of x is equal to 1 over 2 times the square root of x, with the 2 and the radical x in the denominator. So we've got a constant in front of the function, so I'm going to copy that 2 down. The constant is unaffected. The derivative of the square root of v would then be 1 over 2 square root of v. And the derivative of this guy, the number 1, the constant 1, is just 0. So to simplify this just a little bit, we can imagine that this 2 multiplies into the fraction, and it essentially arrives in the numerator here. That numerator of 2 and the denominator of 2 will cancel. They'll factor to 1, and we now have 1 over square root v. This 0 falls off as well. So here's our g prime. So with that known, with those statements made, we can now find the derivative with respect to v of v squared times 2 radical v plus 1. We can now find this derivative. And the derivative, again, requires the product across this diagonal multiplied first. So we could say 2v times 2 radical v plus 1. To that, we would add the product of this diagonal, which is v squared times 1 over radical v. And that's an okay solution. That's a decent solution. That does represent our derivative. We should be cognizant of ways to simplify if we can, but even if we distribute in this group here, we'd end up with 4v square root v. V's and square roots they're giving me trouble here with my symbols here. Plus 2v plus now v squared over square root v. It's not like we have anything that cancels within a fraction, or as we distribute, we don't get to eliminate any radical signs. So this would be an okay answer as well. I think in this particular case, either one would be acceptable, and I bet Math Excel would accept them as well. So why don't you try part B on your own? I know I've taken up some space here, but there should be enough room on the right side of your handout. Tell me, what's the derivative of x squared times e to the x? Pause the video now and resume playback in a moment to check your work. So for me, I labeled the f function as x squared and the g function as e to the x. That would imply that x squared multiplied by e to the x makes the larger function. And the derivative of f is 2x. The derivative of g is e to the x. We just learned about that in the last video, that the derivative of e to the x is e to the x itself. Therefore, the derivative with respect to x of the product of these two functions is the cross product of f and g prime plus the cross product of f prime and g. Now I went out of order here. This time around I wrote the cross product of f and g prime first. I wrote this group first and then this group second. But that's okay since since addition is commutative. It's a commutative operation. We can write those two groups out of order. For the quotient rule, however, that's not going to be permitted. Now the second two results that I've shown here are just the results after factoring. In this first example, I noticed that e to the x power was common to both of these two terms, so I factored out e to the x, and I'm left with e to the x times x squared plus 2x. From here, I noticed that x was a common factor in these two terms, so I factored it out as well. So any one of these solutions I think would be appropriate, and we should be aware of all three of them in case factoring into different forms would benefit us in another way. Or perhaps maybe Math Excel would be leading us to find a solution that has a specific format. I have a few other examples that I'd like for you to practice with, 7, 8, 13, and 14. So if you would, pause the video now and resume playback in a minute to check your work with my solutions. So in problem number 7, that was pretty straightforward. Hopefully you recognized that 3x to the 4th and 2x squared minus 1 are the two functions we can use to find this function's derivative. Now, even though this function is labeled as function f, we could still use this abbreviated notation, f and g, off to the side when determining our components and their derivatives. I think this solution would be pretty good, and this final solution would be pretty good. If you're going to simplify this first answer, I wouldn't stop halfway. I would go ahead and take it all the way down to the end here. For question number 8, this is kind of interesting because I don't think we've seen any of these yet. This is really a combination of two different rules. Certainly finding the derivative of 6x is pretty easy, so I didn't bother to mess with that at first. What I noticed was that the second function over here is comprised of two other functions, 2x and e to the x. And I just realized a typo, so I better fix this here. It was a minus sign. So in this second function, I used the product rule, where 2x and e to the x were my two component functions. Then when it came to find the derivative of g, well, I know the derivative of this term is just 6, so I jotted it down, and then I subtracted the derivative of this combination of functions. And this one was the result of course, of our multiplied diagonals here and here. Now for each of the remaining problems, I am going to try to go in this order because it'll help us reinforce the order for our quotient rule. And I did end up with 2 e to the x power plus 2x times e to the x power. That's a fine answer. If you notice that 2 times e to the x was a common factor, you can factor it out and that would be just as good. And in problem 13, again, I think these two are fairly straightforward. For number 13, I chose the f function to be e to the w power and the g function to be w cubed minus 1. After identifying those components, cross-multiplying across these two diagonals and summing them together, and looking for common factors to help factor or combine like terms, ended up with each of these three answers. Again, I feel that this solution is just fine. If you notice that e to the w power was a common factor between these two groups, you can factor that out. But then you were left with w cubed, negative 1, and 3w squared that should have been rewritten in standard form. So that bottom option is pretty good as well. For number 14, I chose my inner function to be 4e to the t power, and then well, I shouldn't say inner and outer. My first function, 4e to the t power, and my second function, square root of t. Again, using derivative rules that we're starting to memorize now, I was able to identify those derivatives. And the cross products in this order and then in this order, summed together, produced this first answer. This is kind of an interesting factoring technique after I combined this into a single fraction. I noticed that 2 and e to the power of t are common between these two terms. So if you wanted to factor that out, you could, and you'd be left with 2 root t plus 1 over root t, and that would be a decent answer. This one at the very beginning isn't too bad, but I kind of like this one in the middle better since we've combined the product of two numbers into a single fraction here. Now for the quotient rule, you might notice that a component of that quotient rule looks a lot like the product rule. In fact, this section here highlighted in yellow would be the product rule if there was a plus sign here. And so hopefully you recognize the fact that we're using a subtraction instead of an addition makes sense because of the relationship between quotients or division and subtraction as opposed to products and addition. So with the quotient rule, we're definitely going to subtract, and since subtraction is not a commutative operation, then this order does matter. Order matters here. We can't just reverse them. We have to multiply the lower function g times the derivative of the upper function f first. We've got to put that component first. From our original video, the phrasing that I said that might help you remember this quotient rule is low d high minus high d low over low low. If you say that phrase to yourself or come up with a little tune to remind that order, it'll help you memorize this rule pretty quickly. Low d high minus high d low over low low. And let's try an example with that. So here's a function f that is a quotient of two polynomials, and this is going to produce a rational function, something with branches in its function, and we would like to know what the derivative would be. Now I'm not going to take the time, and I don't think it'll be very easy anyway, to actually divide these two and produce a single function like we did at the very beginning of this video. It's just not going to pay off. So instead I'm going to utilize and rely upon the quotient rule. I'm going to treat f, my upper function, my first function in this case, as the one on the top, x cubed minus 4x squared plus x. And you should always treat f as the upper function, the higher function. And g, our lower function, is 2x squared minus 3. Now we would find the derivative of each like we've done in the past. 3x squared minus 8x plus 1 and 4x. And again, the cross products are going to be necessary. We must start with this cross product first. We always start down this diagonal. This is our lower function g times the derivative of the higher function f. This is our low d high phrase. So low d high. And then we'll multiply these two, and that product would be our high d low, the upper function times the derivative of the lower function. So low d high minus high d low. Let's start with that first. Okay, so there we go. The low function times the derivative of the high function. Oops, I was pointing those backwards. Low function times the derivative of the high function minus the high function times the derivative of the low function, all over the low function squared. So 2x squared minus 3 squared. Now, many times in this particular derivative rule, the quotient rule, we will not bother foiling this. We won't expand this binomial pairing. However, in the numerator, there will often be a benefit to expanding this, combining like terms and looking for pieces that cancel. So on the one hand, we are saving some time by not even worrying about the denominator, but on the other hand, this numerator does need some attention. So let's go ahead and do that next. So it's starting to look like the old difference quotient again, doesn't it? After we do some distribution, we start seeing some terms that will combine. Now in this first group, I'll just be real clear here. The way I distributed this trinomial with the binomial is I took 3x squared times 2x squared, then 3x squared times negative 3, and that's how I got these first two terms. Then I moved to my middle term of the trinomial, and then the last term of the trinomial. That's how I accounted for all of those products. I kept all of those products wrapped together inside of a grouping symbol, the square brackets here, so that when I complete the second round of multiplication, I could keep them in brackets as well. And that way I don't have to worry about this negative sign in the middle. I'll just copy it down and I'll worry about what it does later. I'm completing all the multiplication before I worry about any subtraction. Oops, and there was a mistake in my math here. I don't know where that 12 came from. This is 4x times x cubed. That's just 4x to the fourth power. I think that's okay. So for my next result, I'll just combine some like terms. So 6x to the fourth appears to be the largest exponent. As I run through, 6x to the fourth can combine with a minus 4x to the fourth. That'll give us a 2x to the fourth power. Then x cubed, we've got a negative 16x cubed minus 16x cubed. The 24x has nothing to combine with it. I should have marked that off. The 24x has nothing to combine with it, so I'll bring him down. And this minus 3 has nothing to combine with it either, so I'll bring it down. And we have a denominator of 2x squared minus 3, quantity squared. From here, if you wanted to try factoring the numerator in the hopes that you might uncover a 2x squared minus 3 that can be factored from the numerator and the denominator, that would be a good approach. However, I can tell with these two groups, 2x squared is not common to the first group, and 3 is not common to the, well, 3 is common to the second group, but not a negative 3. So I don't think factoring from here is going to benefit us at all. We'll go ahead and leave this as our final answer. So if you've heard me say it before, I'll say it again. The majority of your calculus work is algebra, and you probably noticed me make at least 2 or 3 mistakes. Mistakes are bound to happen, and a lot of times it's not the algebra, it's not the calculus that's giving you the trouble. It's the algebra that goes to support it. So anyway, this video is getting quite lengthy at this point. I'll go ahead and pause it right now, and I'll let you reach out to me if you've got any concerns or questions. Thanks for watching.